Well, it looks like we can begin. Welcome back, everyone. So for today's class, we're kind of doing more of the same. We just had a long section on doing derivative after derivative in section 3.3 with an application mixed in. And 3.4 will do more of the same pretty much. Here we'll be emphasizing new techniques, the so-called product rule and quotient rule. And these will be useful whenever we're dealing with this sort of situation here. Whenever we have, say, a function like this, but we can't necessarily expand out in this nice way, we just must use the product rule. So those are going to be the new derivatives coming up. But as far as the quizzes go, quiz 3 was coming up with the tangent line equation, and you can use the definition of the derivative, or you can use the properties of the derivative itself. So multiple ways to attack that quiz. And for the upcoming quiz 4, it's also based heavily on section 3.3. So these kinds of derivatives are going to help us navigate through those problems there. Because that's not a lot of announcements to start us off, but any questions at all, folks? Okay, maybe one more thing to mention before we jump back to 3.3. The notes here are meant to mostly mirror the kind of problems that you're seeing in WebAssign, but it's hard to make sure that every problem looks identical to every single problem you're going to see on there. So if you feel like there's one that just doesn't really fit into what we computed here, don't hesitate to reach out, either by email, use the Ask My Teacher button, or even just ask about it at the start of class. Starting off with a problem out of the homework WebAssign is always a good way to start off, especially if it's something that just seems a little bit weird and non-standard. But for the moment, speaking of weird and non-standard, let's finish off a few more derivatives, section 3.3. And here's where we left off. I put down a little quick border here, just as a reminder. The major tool that we're going to use on these is this property. The derivative with respect to x, same property that was on Moodle, of x power of n. This could also be indicated by just saying x power of n prime, if you prefer, just the same formula. But for some reason or another, it seems like our author likes to indicate a differentiation formula in Leibniz notation, at least with the first time it's introduced. So that derivative will just be n times x power n minus 1. And this is saying the exact same thing. This is just expressed in Newton's prime notation. That derivative is n x power n minus 1. So one challenge then that we have with this problem here is, well, maybe two challenges. It's a variable s, but just think of this as s power of n. Formula is going to work the same way. Second challenge is there's problems with all of those exponents there. This is explicitly stated with the base in the numerator. So to use that formula without any kind of mental backflips to make sure the negative signs work out, we'll do this strategy right here. Go to every single base involving s, bring it up to the numerator. We'll get -3, s power -4. All we do is we negate the coefficient, negate the exponent. So this one will be +9, s power -3. S is a tricky variable. You want to try to write it in a way that it doesn't look like the number 5. It's easy to get mixed up along the way. And that one's a little bit tricky, but here's one way to think about it. Base s still moves into the numerator. That power 3 you see there becomes negative. And because this is a fifth root, there'll be a denominator division by 5. So that's a good way to view it, but you could also just say, with some scratch work, fifth root, s power 3, is 1 over s power 3/5. So a fifth root just implies a denominator 5. Then bring it up to the numerator, s power -3/5. But either way you visualize it, we're in a great spot. We can now differentiate going term by term. Any questions with the exponent work so far? Okay, now for the next thing, we can call it a prime at s, but the variables are kind of non-standard. Oftentimes when you have these kind of variables, it indicates this might have been an application problem. We threw away the context and we're just differentiating what we see. But in these kinds of situations, when the variables look a little bit weird, oftentimes we use Leibniz notation to indicate the derivative, which would be the derivative of a with respect to s. But that's just a stylistic choice. You can indicate your derivative either which way. The major thing is it's just important to see both notations. That's why we're harping on it a little bit to start off today. So back over here, but really looking at this step, we'll say A prime or dA ds, I'll go this route, is the derivative of this term. And there's a whole trick to doing that. This is expressing power of n comes down and multiplies whatever you have here. So that's going to be a 12. Variable s stays where it is. And this part of the formula says subtract 1. If it's -4, it'll be -4 minus 1. So new power, -5. We should pause right there. Does that make sense to folks on going from that term to that term? Okay, just a weird number game essentially, right? It can look more abstract based off of what the exponents are, whether they're negative or fractions. But at the end of the day, same exact pattern. If there's no coefficient in front like this, exponent comes down. If there is a coefficient in front, we're using the constant multiple rule. The exponent just multiply the -3 for a positive 12. So rinse and repeat, we just move over to the next term. -3 multiplies this, so it's -27. S to the power of 1 less, now -4. Final time, we'll get -3/5 coming down as a coefficient. Multiply S. Subtract 1 just means -5/5. So we get -8/5 altogether. And at this stage, you could do a lot of different things algebraically, loads of equivalent algebraic forms. Some people might bring S back to the denominator. Some people might take this and express it again in radical notation. Really all up to you. If you stop at this line, I will always want to emphasize that's totally okay as well. WebAssign's happy with it. And this is where the calculus ends anyway. I would say you need reasons to do a lot of extra simplification. If there's a larger problem for doing optimization, yeah, we might have to do a lot of things algebraically to this. Because in chapter 4, our goal is to set it equal to 0 and solve it. But for the moment in chapter 3, we're just mainly concerned about getting the derivative. So that's always a good stopping point. Well, we'll try it out again in part D, but any questions so far? Okay, I'd say part E is getting pretty tricky as well. This is similar to one of the problems up above that we did yesterday. One of the problems we had to FOIL things out before we even got started. And this is kind of like the opposite of that. Before we even get started, you have to divide by that root x. So let's do a little bit of algebra just to organize what's going to go on. That root x is implying a power of 1/2. It's going to divide all of these things right here. So I'm going to say, well, it's x squared, but anticipating the division by power 1/2, let's call it x power 4/2. Divide that by root x. We're just happening to write out this way, convenient for us. And then rinse and repeat. Go to the second term in the numerator, 4x. That variable x is to power 1, so we can rewrite it as power 2/2. No change algebraically. Divide by root x again just means x power 1/2 down there. And it's kind of methodical. Go to the next term. It's a -1. Oh, what I did look before I left. Let's put a -1 there. Divide by x power 1/2. Now, all we need to do is get our base x completely consolidated in the numerator. We're trying to mirror the very last problem, and we'll be on our way. It's almost the same problem, right? To just this time it's involving divisions rather than just moving things up. So next line, we're going to take power 4/2 minus 1/2. Power is always subtract in this kind of organization. So x is to power 3/2 on the first term, plus 4. X is the power of 1/2 on this term. And we always say you bring x up when making it negative. But what's really going on here, if we did it on the margin, is that -1 x 1/2 is just the same as -1 times x power 0. Because x power 0 is 1, divide by x 1/2. That means we get negative x power -1/2. We're just taking 0 minus 1/2. Much like over here, we took 2/2 minus 1/2 to get the 1/2. Really, it's the same kind of pattern, even if there's no x there. So we can say that this is minus x to the power -1/2. So we've got it all in a line. That exponent right here looks kind of borderline. You definitely want to try to write it in so it really looks like it's obviously an exponent. And it's not because I'm super picky when I look at your work. It's more, if it doesn't look like an exponent in the next line, we could just get tricked by our next step, not realizing what it's supposed to be. So at this stage, we're ready for the derivative. But one of the things you might have noticed, especially with part E, is sometimes the algebraic steps in the middle are harder than really computing the derivative itself. Any questions whatsoever getting to this line here? Okay, once we're satisfied with getting to that spot, all we want is base x in one spot in the numerator. We use this just a whole bunch of times, 3 times, and we'll get the following. On the first term, power 3/2 comes down, and subtract 2/2, that's the -1. New power is 1/2. Same deal here. This 1/2 comes down and multiplies the 4, so we'll just get +2 altogether after doing the simplification. X is to the power of 1/2 minus 2/2, so -1/2 on that one. And finally, this one comes down and multiplies what's a -1, so we convert this to +1/2. And x is to the power of -1/2 minus 2/2, so -3/2 altogether. So there it is, that's the derivative of this function down to here, and no further work would have to be done. Any questions, folks, on getting through that one?
So I have a question on the signs for the 1 or -1/x to the 1/2. We turned that, yeah. And then over in the orange, we found that it was -x to 1 or -1/2. So would that change the sign to a positive?
Yeah,
Or would it
absolutely.
be
We differentiate that, it would come out as that positive you see right here.
so that stays as a negative in there
Right
and it
here,
wouldn't
yeah.
change the sign?
Oh, I think I see what you're saying here. Yeah. The only thing that would change in sign when we move this base x up into the numerator is just that exponent right there. So the exponent would convert to a negative, but the coefficient in front would just still stay a negative in front, even with the base x moving up.
Okay.
Is that what you were asking about with that question?
Uh, yeah, I was just confused on for the negative x to -1/2, that sign would stay the same. Because on the right side we found that it was -x, but the sign in front of it from the equation before, because a negative, the way I think about it is it's in the parentheses. So it's the negative parentheses -x to -1/2. Would that change the sign in front of it?
That would. So we could put a parenthesis in like that, but we would have to put a plus right here if we did that kind of insertion.
Okay.
And if we put a parenthesis in this way, thinking in these terms, then we wouldn't put in an extra negative sign here. We would just leave the negative sign factored out to the left in that kind of sense.
Oh, okay, yeah. Thank you.
Yep, absolutely. So pretty much what was going on was from here to here, we were just moving around the thing on the inside. So that negative stayed put into that spot. But that's a really good question about these kinds of things. This is really tricky work once we start moving around exponents, changing negative signs around. Other questions at the moment about getting to that spot there or down to here? Okay, thanks for asking about that one, Abby. Well, we're nearly done with these notes. There's 2 more questions, but we did this one right here before we went to call it the end of the class on Tuesday. The idea with this one here is this is a constant. And so we use the property that the derivative of any constant alone in that kind of sense is automatically 0. But if it looked like this for just a slightly different problem, if it was y equals 3 e power 8 times x. Now this is a different rule with a constant. Here, no variable whatsoever immediately implies the derivative has to be 0. But now over here, we have a constant multiplying variable x. This one will give us y prime is just 3 e to the x. Kind of weird in a sense. Any questions, folks, about part G or the slightly different version? Okay. Honestly, I think that this is really confusing to look at. If you feel the same way, because it's just so built up, there's a lot of stuff here, an analogy is really good as far as a problem solving strategy. The analogy is the derivative there by the red dot coming down here is no different than really differentiating 5 times x. What we have here is a really built up constant and just a simpler, easy to work with constant. On the right, y prime would just be 5, whereas on the left, it was 3 e to the x. The whole constant here would survive. But here, variable missing means it's only a constant, so the derivative is 0. So that takes care of part G and 2 other versions. They're good to sometimes see these other versions side by side to spot what is the difference between all of these. And now last one we need to take a look at is part F. Well, we have a formula for that one even. There's an exponential function, and our author provides this awesome tool, the derivative with respect to x, of specifically the base e exponential function, is itself. But then we have a problem, right? When we're looking at this exponential function by the red dot over here, that doesn't really quite fit into this pattern whatsoever. There's no x plus 1, in other words, that's being stated here. So just like on the rest of the problems, we need to do some exponent work surgery on this, and then we can get started. Idea with this one is e power w plus 1 turns out it factors. We get z equals, take e times e power w plus w, and that's the factorization. So the idea with this one is, let's take a look on the right. If you take e times e power w, you can throw in a power 1 on that e, and in this configuration, exponents just add together. So that would be e to the power of 1 plus w, or w plus 1, if you change the order right here. So we can always do that kind of factoring, drop the power by factor out to 1 copy at the base. Now when we go to differentiate, this e power w is going to be differentiated through this rule right here. And there's an e in front, but that's just a constant. It's just like having a 5 in front. Constant multiple rule is just going to allow it to carry down unaffected. Definitely kind of a tricky problem to look at. But after we get to this stage, we can say either z prime, or let's write dz dw, because these are strange variables. This is our way of asserting w is the independent variable that we're differentiating with respect to. We hit it with the constant multiple rule, which just says copy e down. It's multiplying so it doesn't go away. Then we use the derivative of the exponential e power w. That's just itself. And notice it looks like if we did just say e power w plus 1 and copied it down, that would be an extension of this formula, and it really does work. But it's tricky because if it's e power 2 w plus 1, breaks down completely. That is really, really weird. We need another property that's going to help us to see what's going on here when it's a little bit more built up, like w squared plus w. The pattern's going to totally break down. What we need is the section on the so-called chain rule. But for the moment, we can do this derivative here. This whole portion becomes e times e power w. Take the derivative of this w right here. That's just going to be a plus 1. And we did it. That's our derivative of part F. Pretty tricky one to look at because it didn't look like it fits the formula at the very beginning. Well, any last questions, folks, on any one of these problems? Okay, well, we did it. This is the, as our author calls it, basic differentiation formulas. Not all of them are all that basic. This one is a pretty wild one in a certain sense when you think about what the derivative is trying to say, giving you slopes to the tangent line. But for now, what we're going to turn around to is more built-up functions, functions for which we can't expand them and differentiate term by term by term all the time. Functions for which we need the so-called product rule, or the next one, the quotient rule. But there's an immediate challenge with this product rule. The product rule could be used in situations where it causes more harm, makes your problem longer than it needed to be, more complex than it needed to be. And in some situations, it's the only tool you can use. So part of our goal when we introduce something like the product rule, quotient rule, is to say when it should not be used. That's kind of weird. We are introducing a rule and saying don't use it. And we want to say when it should be used. So we want to spot the difference between both of these functions. And this is something that happens in the homework as well. You might be given functions where you don't even really need the product rule necessarily if you possibly just expand out your function. But let's take a look at the product rule. We'll apply it over here just because we might as well use our new rule as we're looking at it. And then we'll differentiate this one without using the product rule. Here's how it goes. It says if you're differentiating a product of functions, f times g, here's the prime right here, the result is going to be two terms, and it's kind of a surprise. You differentiate one function, copy the other, add to it, copy the first function, differentiate the other. It's as if the prime moves across each one of these, but you have to make a new term as a prime goes from function f to function g. If there were three functions, same exact pattern, three terms, and the prime moves from one function to the next to the next. Oftentimes, we're just using two functions, though, when we go to use this formula. In Leibniz notation, it looks a lot more complicated. I usually state this one in Newton's prime notation, just so we can focus more on the pattern, not on this huge smattering of symbols that we see right here. But really, it's saying the same kind of thing. The d dx f of x is just a way of saying f prime, and then g is copied in. For this part, dx g of x is just a way to say g prime, and then we copy the f of x part. The terms are given in different order. That's kind of weird. But in Algebra Plus, you can switch the order in any way that's convenient. I think this is convenient in a real sense, and let me give you a preview of why I think it's a good idea to go f prime g, and then f g prime. Scrolling down the notes just for a moment. When we have both the product rule, this one, and the quotient rule, this one we're going to take a look into next, getting the numerator right can be finicky, actually. So if you do this pattern, f prime g, f g prime, it reduplicates over here. And it's just a really nice way to organize both formulas simultaneously. All you do then is you spot the difference between the rules. In product rule, you go plus. In quotient rule, you go minus. You also divide by the function squared, which is kind of surprising. So that's the difference between the two rules. And it's also the reason why I usually like to write it with f prime first. So back up to the top, let's actually use this rule, see how it goes. This is a function where we absolutely need the product rule. It's not really just a should, it should be more of a, let's say, must. Product rule is just essential on this one, in other words. So what makes it essential is there is no way to expand out this function. So we can separate one term plus another term. These are multiplied and there's nothing you can do about it. They're just essentially coupled in that way. This is when we really need the product rule. And it comes up a lot with the exponential function. Once we have the logarithms in picture, the logarithms often will apply a product rule if it's x times natural log x. Here we're looking at x cubed times e to the x. No possible way to expand. So we must use the product rule. We'll go g prime of x equals, and it's kind of inconvenient to have called this function of g of x and this one of f of x, because f of x, g of x are reused in the formula up here. But the way you want to think about this formula is it's less about the names you call these functions. It's all about the pattern. The pattern is you differentiate the first term. So we'll just drop a blank and say that. copy the second term. Then go to add. Do it all over again, but you're copying the first term, whatever it is, whatever it's called, multiply by the derivative of the second term. And this is the structure. If you get in the habit of writing down the structure each and every time, I think this is the best way to really memorize your product rule, because now you're focusing on the pattern. You're putting in a whole bunch of blanks, which just makes it a lot easier for our brain to see what goes where. Go to the first factor, x cubed. It goes into the first positions on both terms. Go to the second factor, e to the x. It goes in all remaining positions. And now let's just briefly check if we match the pattern. We need to differentiate the first function. First function is x cubed, and there it is differentiated. We need to copy the second function. Here's e to the x copied. Copy the first function. There it is. Differentiate the second function, and there it is. Well, that's a nice derivative. That's just e to the x, but we put the prime there just so we can memorize the pattern and get it down right. Now, next thing, we have to actually do the derivatives. So we'll say g prime at x equals, here we're using the properties that we were looking into in last section, 3.3. Derivative of x cubed, just a 3x squared. Copy e to the x. Copy x cubed over here. Derivative of e to the x is itself, so we just put in an e to the x. And at that stage, we're done. That is our derivative. You could factor some stuff out. Looks like x squared e to the x factors out. But like we said before, it's okay to leave it in this format right here. We would need a reason to want to factor this out. Chapter 4 would supply those reasons when we get there. Well, we did it, folks. That's the product rule. Any questions whatsoever running through those steps there? Okay. Over here, product rule absolutely works as well. And you will never lose points if you did use the product rule on that one. There's no harm. You're going to get the right answer. The only harm is if you did use a product rule every single time a product comes up, you're working a lot harder than you really ever had to. So sometimes being a little more accurate with doing your derivatives means find the easiest way to do it. It's highly encouraged. There's no reason to take unnecessary steps when you don't need to. This one expands. And that's the only reason we're not going to use a product rule. Product rule is not super complicated, but there is a lot going on here. But what we're mostly familiar with, more than the product rule, is just expanding out an expression like this. So let's go back to just ordinary algebra. FOIL out that thing, distributed x first, 2x squared, minus x, distribute 3, plus 6x minus 3, consolidate like terms, and we have 2x squared plus 5x minus 3. But from this stage on, the derivative is immediate, f prime of x. No product rule here because that's a constant. We're using the constant multiple rule. We just differentiate as normal. 2 comes down and multiplies, giving us a 4. X to power 1 less. So now power 1, which we just write as x. Here, this becomes just a plus 5. The power 1 multiplies the 5, no change. New power 0, but that just means x is canceled out. The derivative of the constant goes away. So it's all just a 4x plus 5. Again, you could hit it with the product rule, but you have a lot more steps, a lot more combining like terms. You get to the same spot either way. Well, any questions at all, folks, with either versions there? Okay, well, with those two examples down, next thing we're going to do is just practice using the product rule. So that's what these problems down here are all about. Some of these problems are pretty similar to the ones you're going to be dealing with in the WebAssign homework system. And like I mentioned before, sometimes you do just want to hit them with the product rule. Other times, just look before you leap and decide, do we really have to? Well, first thing that's awful about this problem right here is the base is in the denominator. So whether you're using the product rule or not, I think it's still a really good call. Write this as 3x power negative 1 plus 5 x power negative 3 times x minus 1. And now that we get to this stage, you know, it's not too different than the problem that we were looking at that we avoided the product rule on. We could just FOIL this out and get to an answer right away. Or we could use a product rule, there's no harm there, it's just more algebra that's really necessary. This one requires the product rule, so I propose let's just expand this out. Does that sound all right to folks? Okay, it is kind of strange algebra because we're FOILing out with negative exponents. It's not super familiar, so I'll take some extra steps with this. It's 3x power negative 1 times that x right there. You could say it's x power positive 1 because these will combine. But then it's x power 0. That's just a cancellation right away. That's just 3 on the first term. Then multiply this against negative 1 minus 3x power negative 1. And now distribute this. Plus 5 x power negative 3 is multiplying this x. And again, you can leave it just like that, but for help with visualizing the exponent rules, you can insert a power 1 if it's helpful. Then multiply this against negative 1 minus 5x power negative 3. One extra step. These two cancel. We have a 3 here, minus 3x power negative 1. We can combine the bases on this one to plus 5, x power negative 2. And nothing much to do on this one, just minus 5, x power negative 3. So kind of a weird problem already because we didn't use a product rule, we just expanded the product. But now, differentiating y, let's call this y prime, now we're in the derivative. Whereas over here in black, we're just re-expressing the original function. First term is gone. Constants always vanish when we differentiate. So we move on to the next term. Negative 1 as an exponent multiplies negative 3 for a positive 3, and drop the exponent 1 value lower. Now negative 2. Rinse and repeat. This will be a negative 10, x power negative 3. And last, negative 3 multiplies negative 5 for a plus 15, x power negative 4. At that stage, we've got it, folks. We avoided the product rule, and I think this is as fast as you could do this one. It's not that the product rule is bad, but if you can avoid it, it always implies a little bit less work, I'd say. Well, that's one down. This one, we cannot avoid the product rule whatsoever, so we have to work a little bit harder. But any questions at all, folks, getting through this one? Okay. Well, let's add a little extra note here. Product rule is not necessary. We can just expand. But over here, product rule is required. There's no way to expand 9t cubed to e to the power t, at least not in the way we expect. E to the power of t can be written in different kinds of ways, but no ways are really helpful for us taking the derivative. So we're going to just immediately say f prime of t. We're dropping down into the derivative. Like we mentioned before, it's all about the pattern here. So let me write it out this way. It's going to be equal to a prime here, no prime on this one, we're copying the function, go plus, no prime on this one, that's a copy. On this one, we copy it in, but then we differentiate it, so throw in the prime. If you kind of like the strategy of just making placeholders and dropping stuff in, then definitely don't forget those symbols there, because this is your reminder you have to differentiate that factor. And sometimes you'll remember, but if you never put these in, good chance that you might just forget one time. So this is for the sake of safety. Now we go back to our terms that we see over here. We can think of this as the first factor, 9t cubed. We can think of that as the second factor, e to the power of t. So then drop this here, 9t cubed. For e to the power t, we can drop it into this location and this location. And this is just one way to do it. You could have actually taken that 9, left it factored out way out in front. But this is a nice way to visualize, just taking that whole chunk and dropping it in there. Not a bad way to go either. So different routes to get to the same place on this one. Well, once we get this structure down, we're just about done, but we never want to celebrate early. We definitely have to still differentiate here. So this will be at 27 t squared. Copy this one. Copy this one as well. And differentiate e power t. It's kind of weird. Nothing happens, just e to the power of t. And you know what's kind of weird with us so far in this section is that the product rule, you might notice, is only really coming up when an exponential is inserted into the problem. That's because have a strange prerequisite for our course. We don't cover the trig functions because it was not our prerequisite whatsoever. But the trig functions cause product rules to occur all over the place. For us, just e power t. That's kind of weird. We'll get a logarithm in the upcoming sections that we'll differentiate. If you're curious how that goes, let's just put a preview. Derivative with respect to x of natural log x. This is a nice derivative. It's 1 over x, kind of a weird one. We'll discuss that more as it comes up. But this is a down the line later on. Once we have that derivative, it'll interact with the product rule in other new interesting ways. Well, so far we've done a non-product rule, a real product rule on this one, and this is kind of a borderline case. You could expand this out, but if you do expand it out, there is still a product rule inside there when you take the 2x times 4e to the x. So in this case, I don't know if there's really as much value in expanding this one out if you're not skipping out of the product rule. We'll just say for this, because there's going to be a product rule required at some step point, do that. Need to avoid using that pencil tool. That's really weird how it's slow. Product rule is required for that spot there. So let's just hit the whole thing with the product rule altogether. We'll go g prime at t equals, here's the structure. And I think this is always a good emphasis because I myself sometimes forget to put a prime on those. And then if I do forget to do that on the next line, I could be in jeopardy of just totally forgetting to differentiate. Next, we organize. We're using a product rule because there's two factors and they're both non-constant. So drop in this first factor into all the first parentheses here and here. 2x minus 9 and 2x minus 9 on that one. Once that's filled in, you just go to the second factor and it has to live in all the remaining placeholders. 4e to the x plus 1, 4e to the x plus 1. So there's our product rule. Last step is just to differentiate as normal. So g prime at t next is, hang on, I think I have a mistake here. I'm looking at a g at t, that should have jumped out at me. If that's a g of t, but there's x's over here, our derivative isn't quite right. Let's make a quick correction here. I hate to fix a typo after the fact we were looking at the notes, but that is a worthy typo to pause on and correct immediately. That should say g prime at x. And that's such an important correction. Let's put in red to indicate there was a mistake there to avoid. That should be x as well. The reason that's such a big deal is, let's put this out in a box over here. If you say g of t, let me go to a different color here. If you say g of t is 2x minus 9, or e to the x plus 1, and then you go to calculate g prime at t, the surprise here is it is now 0, because if you put in a variable t, that's the independent variable. It did not show up here, so these x's are considered constant with respect to differentiation. So that was actually a pretty major typo. If this was an exam question, I don't think I could have actually allowed that to be part of the exam. It would have had to have been thrown out of confusion. But does that make sense to folks what the issue is here and what would have happened? Okay. Well, now back to the correct notation, we're taking g prime at x. Here, we just differentiate x. Any volunteers to say what that derivative should be? I heard it too. Yes, absolutely. The -9 vanishes because it's a constant, not multiplying anything. That's a constant multiple rule. And x power 1 vanishes when we differentiate. So good call, just a 2. Over here, we copy in everything we've got, 4e to the x plus 1. Another set of copying, 2x minus 9. But on our last one here, something does happen. Anyone have the derivative for this part? Absolutely. Here, it's a constant multiple rule, 4 stays. Derivative of e to the x is itself. Plus 1 goes to a 0 upon differentiation. So just 4e to the x like you said. And we've got it, folks. You could distribute in the 2, distribute in the 4e to the x, do a whole lot of work on this. But if all we're doing is calculating a derivative, I would be okay if you stopped right at that spot. Any last questions, folks, on getting through down to part C? I think that's the last of those. Okay, so that's all about product rule. Now we're going to turn this over to the next thing, quotient rule. Major thing about quotient rule now is the numerator is almost exactly the same when we go to use the product rule, except there's a minus in the quotient rule, and you divide by the denominator to the power 2. So those are the only real changes when we go from product to quotient rule. And there's a really cool analogy here. It's an algebraic analogy, but I think it's a good one because we're going to get into logarithms at some point pretty soon in chapter 3. Logarithms have 2 types of rules as well, called a product rule and a quotient rule. The natural logarithm of a product, a times b, is the natural log of a plus the natural log of b. Really logarithm to any base. I just wrote natural log because it's faster to write in. And if we go natural log a divided by b, we get natural log a minus natural log b. So these are pretty important formulas. We're going to use them a lot when we get into the section on logarithms. But it's nice to see that it kind of matches what we're doing. If there's a product here, you should be using a plus. If it's a quotient here, you should be using a minus. And same thought with product rule, quotient rule. Quotient rule comes up, throw in a minus, and don't forget there's a denominator, and you're all set. But just like we mentioned before, quotient rule is more complicated than the product rule. It's a whole fraction you're getting. And so we really want to pay very close attention on when you should use it and when you should not use it. Let's actually do this one first. It's kind of surprising because, I try to come up with functions that look almost identical. So if you can train your eyes to spot the difference right here, you'd be saving loads of time on calculating your derivatives. So the difference on this one is you can expand this. Well, expanding just means divide all the terms by x. So this expands. And so we get x divided by x plus 1 divided by x. Simplify the first term to a 1. Bring the base x up to the numerator for x power -1. And all we're really doing is just differentiating this. Fast derivative now. That constant goes to 0, so we don't have to write in anything. Here, power -1 comes down, new power is -2, and then we are done. That's as doing this derivative as fast as possible. Doesn't work over here. It's kind of a surprise. Algebraically, if there's an x plus 1 in your denominator, this does not expand. That deserves an exclamation mark. And I'm really thinking I should change my wording here. That should say, in this case, the quotient rule must be used. Must is a really strong word in mathematics, but I think it fits in this case. We must use a product rule to get through that one there. Well, you could use long division, but no one wants to get into that. We want to differentiate this right where it is. So here's the structure. The thought is, it's not about f of x or g of x in the problem. It's On the last one, when we were doing product rule, it was first factor and second factor. Now that it's the quotient rule, it's about analyzing the top function and the bottom function. If f is on top, it has to be differentiated right there. If g is on the bottom, it gets differentiated right there. And then we square the bottom in that way. G of x, f of x are just copying into those spots. So down over here, in calculating g prime of x, first thing we want to do is just lay out the structure. This helps a lot in memorizing how this ought to go. There'll be a prime, copy, a minus. That one's easy to miss, especially after practicing product rule. So minus goes there. Another set of copy and a prime. Now, new thing here, we have a denominator raised to power 2. But once we identify that the top function is just x, we'll go into this location and this location. So think of f of x in blue as just x. It drops in here and in here. Once you decide where the top function goes, the bottom function x plus 1 goes everywhere else. So resolve where the top function goes, and it makes copying the last steps a lot more immediate. So there it all is. We still have two derivatives, so we have to do the derivative here. Let me make that just a little more apparent. And the derivative there. The derivative of this one is 1, and so is the derivative of this. So not too much happens beyond this point. We get 1 times x plus 1. Here it's going to be minus x times 1. The times 1 is from this derivative. And the denominator, we're going to duplicate a comment that we mentioned last class. It's usually not a good idea to do much with the denominator. In its expanded form, in its factored form is its most useful, because there could be a chance something cancels in the numerator. Leaving it in its factored form is our best way to identify that. But does it look like anything cancels? This is 1 times x plus 1, so just x plus 1. Then minus x, divided by x plus 1 squared. That means the whole thing is just 1 over x plus 1 power 2. So that's how the quotient rule goes. Numerator is just like the product rule with a minus, and then don't forget to square whatever the bottom function was. And then we're not doing anything too different beyond that point. Well, any questions at all, folks, with those two examples there? Okay, I want to add maybe just one more example here. On this example, you can use the quotient rule. And like we mentioned, it's not going to hurt you, other than it takes additional time. But this is one where it's starting to use up a lot of valuable time. If you have a function g of x equals, say, 7 over x cubed, we saw in the last section how to handle that. You just want to bring the base x up into the numerator and then work it out. If you use the quotient rule right here, you get the same exact thing, but you have a lot of extra steps to work through. So write this in as 7 x powered negative 3, and that one simple step, moving the base x to the numerator algebraically, has taken us away from that whole process. It's absolutely worth it. So g prime of x on this one is just negative 21 x powered negative 4. The negative 3 by 7 gave us the negative 21, and we dropped the exponent 1 lower. So that's the big warning with the quotient rule. It can be easy to get bogged down in problems like these two right here, when it was never really the intention for it to be a longer process. So always look for the easier way out when you can, but try to look for the problems which forces us to do a quotient rule. It could be because this happened. There's no way to expand this out if there's multiple terms in a denominator. Well, I think we're ready to practice out some more standard looking homework questions. Those are the ones down here. We'll take a look at 2x plus 1 over x plus 3. It's a little bit harder with an exponential, a little bit harder with another exponential. Then we'll kind of consolidate all of our formulas into one spot, do a couple problems where we're just practicing those formulas. And we may not get to this one today, but when we come back on Tuesday's class, we'll look into a really great application for when you really need a quotient rule. Looks like this one is coming from engineering. So let's go back up to the top. And now we're just doing derivatives as normal. But when you look at that one, I believe we've done this one before. Let me double check real quick on the Moodle website. In section 3.2 or 3.1, I forget which, we did some rather tough derivatives. Let's take a look. I think it was possibly this section. 2x plus 1 divided by x plus 3. We have differentiated that before, and we did it strictly through the definition. It was a humongous process, but we landed on 5 divided by a plus 3 squared. We're doing f prime of x, so we should get 5 divided by x plus 3 squared. So keep this unsavory approach in your mind, and it's a really strong sell on why we want a quotient rule. Let's give this one a try next. There's two functions. Because the denominator has two terms, I can't expand this out and sideline the quotient rule. It's a feature of this problem now. So I'm going to think in terms of a top function versus a bottom function. Call the whole thing y prime. And this is just laying out the structure to get started. Okay, every single quotient rule, looks about like this, but I did make one mistake. That's a legitimate mistake. That should be a minus if you're doing the quotient rule. So don't do as I did. Be sure to put a minus here. I guess it deserves a comment. Minus for quotient rule. More of a reminder for me at that point, I think. But now let's start dropping in what we've got. Settle where the numerator goes, 2x plus 1 in this first position, and the next term, this first position. And now you know where the denominator, x plus 3 goes everywhere else. So here, here, and here. Beyond this point, we're just differentiating these terms as we see them. The derivative of this one, 2x plus 1, is just a 2. Copy in x plus 3 minus 2x plus 1. The derivative of x plus 3, that's just a times 1. I'll keep the color coding whenever we actually did a derivative to show that's what we did over here to go to here. I'll convert it back to black when we're just copying from the last line. So all this is now divided by x plus 3 squared. I know the numerator does simplify in kind of a nice way, so let's expand out, distribute 2 through, 2x plus 6. That times 1 can be thought of as just not being there. It cancels, doesn't change anything. We're distributing in really a negative 1. So minus 2x minus 1. Down below is x plus 3 squared. Numerator, like terms, 2x minus 2x cancel, so we just get a 5. And we have x plus 3 squared down below. Taking a look at what we did before, that's exactly what we got. Only difference is the variable is a rather than x. But this was a real process doing it from scratch. And this shows the value of a good theorem. A good mathematical theorem, its role is sometimes just to help you compute in a rapid way. So we did it, folks. This took about maybe a 20th of the time it took to do it from scratch with the definition. Any questions at all getting through this one? Okay, let's try it out again. Really, once you get the pattern of the attack down, it's really all there really is to these kind of problems. So go f prime of x equals, write out this to start. And this time I remembered minus, but this is highlight worthy, I'd say. Okay, we've got our structure. So every time we do quotient rule, that comes up. E to the x, being the top function, goes in 2 spots. Finally, e to the x plus x goes in the remaining. And from here, all we do is differentiate to what we've got. Does that look right to folks so far? Awesome. Some of the derivatives are pretty straightforward. For example, derivative of e to the x, just itself. So there it is. That multiplies e to the x plus x minus e to the x. And we have to be careful with this derivative, actually. When we go to differentiate it, we get e to the x plus 1. But the thing that causes some trouble that we have to be careful of is this derivative involves two terms, so parentheses here are required to get the right algebraic form. So required parentheses. Then down below, e to the x plus x squared. And we've got it, folks. That's a pretty good derivative already. If we decide to simplify this thing, there's a couple approaches. Distribute e to the x into the groups. Different approaches factor e to the x out of the group. If you left it in this form right here, again, I wouldn't be too picky about that. But one of the things we're going for in the next chapter is solving this, f prime of x equals 0. The reason we're so concerned about solving that is because the derivative is the slope of the tangent line. Finding out where the slope of the tangent line is 0 is finding the spots where the curve does this, or maybe where it does that. It's finding a local maximum or a local minimum. So because that's such a common equation, I want to emphasize first, that's a good stopping point. Let's actually practice factoring this just to get a preview of what we're going to be doing in short order in chapter 4. So this is full credit, but we're going to keep on going anyways. Again, it's for a good purpose. Think of these next algebraic steps as a preview. On the next step, e to the x factors out. It leaves behind this group, e to the x plus x. When we factor out of this term, it leaves the negative sign behind, and it also leaves this group, e to the x plus 1. Denominator is e to the x plus x squared. No cancellation with this e to the x and that one down below due to the exponent. But inside here, we can distribute the negative sign in that group. It's e to the x plus x, distribute the negative sign for minus e to the x, minus 1, e to the x plus x, power 2, almost there. And finally, over here, all I'm doing is combining the like terms. E to the x cancels out inside that group, leaving e to the x on the outside, and looks like just an x minus 1. Whole thing is divided by e to the x plus x squared. So we did it, folks. Not only did we do the derivative, it's right here, full credit if you did stop on that spot, but this is the derivative in its most simplified form. So you don't have to do that, but again, we're going to be doing that in chapter 4 quite a lot. We need to get our derivative as simplified as it's feasibly possible because, like we mentioned, we want to take that, set it equal to 0 and solve. Let's actually do it right here just to get a feel for why we want to work on that kind of process. If we set f prime of x equal to 0, the only feasible way, here's f prime of x by the red dot, but the only way a fraction ever takes on a value of 0 is if strictly the numerator is 0. So we grab that part and say f prime of x equals 0 implies e to the x times x minus 1 is 0. Now we solve this equation. It's in a factored form, so it splits into two equations. E to the x equals 0 or x minus 1 equals 0. And then that one has no solution by the red dot because e to the x is greater than 0 for all x and r. So no solution on that one. But that one has a solution. Add 1 to both sides. X is going to be equal to 1. We're going to later on call this a critical number. And the thought again is that it's easy to lose our way with these derivatives because we're doing so much analytical work on it. It just looks like symbol pushing pretty much, right? But there is always some big geometry underlying all of this. For this function here, the moment you calculate the derivative down here, specifies the slope of this function's tangent line at every x value. And that critical number tells us right at x equals 1, tangent line is horizontal. Let's take a look at just what that looks like then. F of x, e power x, divide by e power of x plus 1. And it says here, right at x equals 1, hang on. Right at x equals 1, I should have had a maximum, I thought. I might have made a mistake somewhere on here. Let me double check my work. I might have to come back to this thought right here. Let's see. Anyone notice anything off about any of this algebra here? Getting down to that step. Feels like I might have made a mistake. Could have been the factoring stage. I factored out these e to the x, placed it here. So e to the x plus x should copy in. That looked good. Negative e to the x plus 1 should copy in. Then we were going x minus 1. Huh. You know, I might have to return to the drawing board on this one. I think I had some homework across this weekend. I was expecting a maximum to this function at x equals 1, but didn't find it this time. That's kind of surprising. I'm going to need to come back to here. Maybe a little bit more fresh to see what's going on with that one. I think we've got the right derivative though. Anyone spot anything weird about it, or does that look about right? Okay, well, I think we have time for one more derivative and then we'll call it a weekend. This is a homework problem for me. Let me put a quick reminder. I find all caps makes it an excellent reminder. Come back to quotient rule. Problem part B. Okay, I'll report back to you on what I find here. My expectations just didn't go about the way I was planning. That's always a little bit weird. But aside from that one, let's give this another try on part C. Sorry, question first. Well, sorry, -1 where? Is my red dot about where you're looking?
Um, no, I was looking at the most simplified.
Oh, gotcha.
There's anything to the 0 power is 1, so it'd be 1 times -1, and then, oh, like this would be -1 half, right?
Where are we looking?
1 plus 1.
You're doing the work right here. Gotcha. So another look on that one, the e to the x's would cancel off, right?
Mhm.
That
So I
would,
was looking at the 100,
oh, so this one right here?
under.
Oh,
So the
that
most
one.
simplified, yeah,
Gotcha.
so e to the 0 power would be 1, right?
That is true, yes.
And then it would be 1 times -1 over 1 plus 1 squared. So the quarter.
I guess I'm getting lost on the e power 0.
Yeah, that equals 1, doesn't it?
Yeah.
Then it equals 0 power.
Mhm.
And then it would be 1 times 0 minus 1 in parentheses at the top. And then the bottom would be 1 plus 0.
Oh, so you're just plugging 0 into that whole thing. Gotcha. Let me take a look at that. So if we go f prime at 0, yeah, that would turn into e power 0. And just a -1 here. 1 right here plus 0 squared. And then all of that looks like it's just -1 altogether, is what that would say.
Is that what you're talking about in the box?
In the box, what I was trying to do is take just this whole thing, set it equal to 0 and solve. So I was saying the entire fraction equals 0, which meant the numerator itself would be set equal to 0. And so I split it off into these two different equations to solve, over here and over here. So over here, we're looking at just the evaluation of the derivative. Whereas over here, we're looking for the value of the x that results in a 0 derivative altogether. But that was kind of a weird side topic since it didn't quite go out towards my expectation. But yeah, you're absolutely right. This as a derivative would come out as a -1. I feel like this problem got kind of involved. But we put a little box on this one to say that was the answer to this problem. And that would have been full credit as well if you did stop right there. But does that answer your question about, or your comment about that as well? Gotcha. And now that we're looking at that, f prime at 0 is -1. That's the slope of the tangent line to the original function at 0. Let's see if that pans out. You know, that would be a positive. Hang on. I think I find my mistake. X should have gone there. Yeah, right at 0, that has a negative tangent line slope. It goes through like that. So that actually works out. And then right at 1, I should have a minimum. Let's take a look. If I go right to 1 at 7.3106. A local minimum means to the left, it should be higher. 7.326, 7.34, and right here, it hits a local minimum value, 7.3106. Actually, this did work out. Right at x equals 1, we have a local minimum right at that spot. Let's see if we can really zoom in on that. So we'll go negative 1.1, 1.1. Oh, negative, let's go 0.9, I think is what I was trying to do at 1.1. There we go. So if this is our region we're concerned about, my claim is right here at 1, that's a minimum. Kind of hard to see though, right? The curve is so flat in that region, but 7.31059 to the right here, 7.3106. So it increases to the right, increases to the left. So that critical number really did lead us to a local minimum, but kind of hard to even see it on this function. Why is that important? Well, this could be representing anything. Maybe it's revenue. The minimum would say, well, you have a minimum revenue right there, not so exciting. It could be representing, say, the growth rate of a certain species at over time. Minimum there would be its minimum growth rate, or anything along those kind of lines. But this was a kind of interesting side topic. Glad that we talked about it a little bit longer just to see what's going on with it. And for the next one, let's give this one a try. Again, this will be our last one for the day, part C. That's kind of a doozy as well, because if you really look at that, kind of a lot of stuff going on with this one. If we were to differentiate G, we'd start by just first putting down the structure. It's a quotient rule, so it goes something where we differentiate, copy something minus another copy, something here where we differentiate, and something in the denominator squared. So take x e to the x plus e to the x rather, goes into just those positions. Take 1 minus x e to the x. It goes here, and here, and finally here. So that's the whole structure for the quotient rule. We're differentiating two more things. This derivative is not too bad. You can go term by term. Derivative of x is 1, derivative of e to the x is itself. But this one, not as friendly. Here's the reminder that we mentioned last class that every single differentiation formula we pick up can be connected and coupled with another differentiation formula. This starts with the quotient rule because it becomes a quotient when we take the derivative. But then right here, out of nowhere, that's a product rule. So we have a problem inside a problem. It's like two problems duct taped together. If this happens to you, a good strategy is divide and conquer. A product rule is something we're already learning in the first place. So let's separate that out as a problem, figure it out on the right, and then we'll just plug it back in, whatever it comes out as. So 1 minus x e to the x prime. You know, it's not just a product rule. It's also the difference rule and the derivative of a constant rule. That would go to 0 when we differentiate. And we can think of that whole thing as our first factor. That is our second factor when we go to hit it with the product rule. So here's the derivative starting. Derivative of a 1 is 0. Then we'll go plus. From this part, that's where the product rule begins in earnest. So here is our structure for the product rule. Practically do the same thing over here, but a lot more streamlined. There's no denominator. It's kind of nice. Take your first factor, negative x, throw it into those first positions. Then take your second factor, e to the x, put it in the remaining spots. Now, 2 more derivatives to work out over here, and then we can finalize the larger problem on the left. Any questions at the moment to this stage of this strategy? Okay, so we have from that derivative, just a -1, multiplying e to the x. On this one, it's minus x, multiplying e to the x. We got to love that derivative. No big change on that one. And it could be slightly simplified by calling it negative e to the x minus x e to the x. Other things you could do, you could factor out your e to the x if you like. But all we're really going to do is take all of this and plug it in right here. Well, any questions, folks, on getting to that step with product rule itself? Okay, let's work out the rest of it. So differentiate this one. It's a 1 plus e to the x. Copy just over here, 1 minus x, e to the x. And really your strategy when the math gets this kind of overwhelming, so much stuff going on is, don't look at the whole forest, look at the tree. Just go methodically, one thing at a time. Copy in the negative sign. This one's a copy, x e to the x. X plus e to the x. I keep saying that in a weird way. This one was involved, so we did it on the right on the margin. We're just dropping that in. Negative e to the x minus x e to the x. Finally, we're copying in the denominator, 1 minus x e to the x. And at this stage, if you left it in that part, in this form rather, no harm done. I would understand. This one takes a while to actually fully expand out, to combine all the like terms and get in a nice simplified form. So this is a decent stopping point if you did stop here. If you did do more work with it, you're basically doing chapter 4 stuff. This is the stuff here we're taking a preview of. Setting the derivative equal to 0 and solving is the only reason you really would want to expand this out and combine like terms. But this will be a good stopping point for us today, I'd say. Any questions at all, folks, on surviving this one? Okay, not too many like these, but when you hit this one in the homework, if it seems kind of weird, if it's not working out, don't hesitate to reach out. I know it's a pretty tricky one. I'll be very happy to help out. But have a great weekend, folks. Try not to work too hard. We'll come back to this on Tuesday's class. Oh, and I have something I owe you. Here you go. Yeah, that'd be just fine. Absolutely. If you need additional time, you're also welcome to just take a cell phone picture or scan and send it to my email. That works just fine as well.
Okay.
Yep. Take care. Yep, have a good one.